Welcome to the deep dive. Today, we are getting into something really fundamental. We're tackling a question that honestly feels a bit audacious.
It definitely pushes boundaries.
What happens if the ultimate speed limit, the carrier of all cosmic information light itself, isn't quite as constant as we thought?
Right, that famous C, the speed of light in a vacuum.
Yeah.
It underpins, well, everything in modern physics, really.
Yeah,
Causality, space-time.
exactly. But today, we're stepping into purely theoretical ground. We're going to unpack a framework connecting some amazing real-world physics experiments.
The ones where they actually manipulated light speed.
Yes, and connecting those to these, well, large-scale weirdnesses in human memory, collective memory issues.
It's a fascinating link. The focus is a paper by scientific investigator Justin Lake titled The Hau Correlation, Quantum Interference, Information Coherence, and Collective Memory Divergence.
Quite a title. And our mission here is to really dive into this theoretical framework he lays out. It's this impressive intellectual structure using quantum optics to kind of model cognitive stuff.
Yeah, and Lake's core idea is purely conceptual. It's important to stress that. But it's built very rigorously. He takes the science of controlling light pulses.
Which is real, established science.
Absolutely.
Yeah.
And uses it to build an analogy for something he calls information fidelity. The argument goes, look, if you can stop light, store it, get it back again, you've shown incredible control over how information moves.
Right.
And that control itself highlights how sensitive that information might actually be during its journey.
Okay, let's try and lay this out clearly because it's complex. The key statement, the sort of guiding principle for Lake's argument and for our discussion today is this. The paper proposes that if information encoded in light can be slowed, stopped, or even just phase shifted, then it is conceptually possible that the quality, the fidelity of that data could be altered during its travel. And that provides a scientific analogy, a way to think about how these widespread historical or memory discrepancies might actually happen.
Exactly. It's a model for how such an information drift could be structured. It is absolutely not claiming a direct cause and effect. This experiment caused that memory glitch. Not at all.
That's a critical distinction. We need to keep that boundary clear throughout.
Essential. Lake is taking very precise, measurable physics, the quantum control stuff, and basically asking, okay, if information is this potentially delicate at the quantum level, what are the implications when you scale that idea up to global systems, interconnected networks, human memory, digital systems?
So he's using physics almost as a language.
Precisely.
Right.
A language to describe a potential systemic vulnerability in information itself.
Okay, let's ground this. Where did the experimental physics underpinning this theory even begin? It starts with needing a state of matter that's just bizarre. Bose-Einstein condensates.
BECs.
Ah, yes, BECs, often called the fifth state of matter. And getting there is, well, it was a Nobel Prize winning achievement back in '95 for Anderson, Cornell, and Wieman. It's not just about getting things cold. It's a thermodynamic masterpiece.
How cold are we talking? We're talking temperatures just billionths of a degree, nanokelvins above absolute zero, colder than interstellar space. You typically take bosonic atoms like rubidium and cool them using lasers and magnetic traps.
Wow. Okay, so colder than deep space.
Yeah.
What's actually happening to the atoms when they get that cold? It's not just freezing?
Yeah,
Right.
not at all. As they get incredibly slow, their quantum nature starts to dominate. Their de Broglie wavelengths, the sort of wave-like aspect of each particle, get longer and longer.
They spread out.
They spread out, and then they start to overlap. And when you hit that critical ultra-low temperature, something amazing happens. A phase transition. The vast majority of the individual atoms essentially lose their identity and collapse into the single lowest possible quantum energy state.
So they stop being individuals.
They act as one, like a single giant macroscopic quantum entity. Everything is described by one single coherent wave function. It's perfect quantum synchronization.
Instead of a bunch of tiny chaotic particles, you have this unified quantum blob.
That's a decent way to put it. And that perfect order, that quantum coherence, is absolutely essential. Without it, the light experiments we're about to discuss just wouldn't work.
Why not?
Well, think about light hitting normal matter. Atoms are jiggling around randomly, absorbing and re-emitting photons in a messy, unpredictable way. But in a BEC, that perfect quantum lockstep allows for these highly controllable, frankly weird interactions of light, interactions that are impossible otherwise.
And this perfect coherence, this quantum synchrony, is what enabled Lin Hau and her team at Harvard to do the unthinkable, to fundamentally mess with the speed of light. First reported in 1999.
That 99 paper sent shockwaves. slowing a pulse of light down from, 300 million meters per
Just a
second
universal constant.
down to about 17 meters per second. 17, like bicycle speed.
An 8 order of magnitude reduction. It's almost impossible to wrap your head around, controlling a cosmic constant like that.
It truly is. And the method was ingenious.
Yeah.
It wasn't like shining light through thick glass or something simple. It relied on this really delicate quantum optical effect called electromagnetically induced transparency, EIT.
EIT. Okay, how does that work?
It's the core trick.
Yeah.
You need two lasers interacting with the BEC. One is a weak signal laser, that's the light pulse you actually want to slow down. The other is a much stronger control laser.
Okay.
This control laser is tuned very precisely to interact with a specific quantum energy level transition within the atoms of the condensate. When you shine this strong control beam through the BEC, it creates a quantum interference effect, a superposition of atomic states, sometimes called a dark state, which basically makes the atoms unable to absorb the photons from the signal laser.
Wait, hang on. So the signal light is still going through this dense cloud of super cold atoms.
Yeah.
But because this other laser, the control laser, is on, the atoms suddenly become transparent to the signal light.
Exactly.
Right.
Transparent. But, and this is the crucial bit, the information and energy of that signal, light pulse don't just vanish, it gets converted. The light pulse effectively transforms into a hybrid excitation, part light, part matter. It's called a dark state polariton.
A polariton?
Yeah, a quantum mixture. Most of the energy gets stored in the collective excitation of the atoms themselves. And because atoms are heavy and slow compared to photons, this whole polariton, carrying the light's information, crawls through the BEC at that incredibly slow speed.
Okay, that explains the slowing. But they didn't just slow it down. Hau's team went even further a couple of years later. In 2001, they stopped it.
That 2001 paper is really the bedrock for Lake's conceptual leap. They managed to halt the light pulse entirely.
No.
By turning off the control laser beam at just the right moment, while that slow-moving polariton was fully inside the BEC.
Okay, so what happens then?
The light component vanishes completely. But the information signature, the exact shape, the phase, the frequency, the amplitude of that original light pulse gets perfectly imprinted onto the collective spin states of the atoms within the condensate.
So the light is gone, but its message is encoded, like written, into the BEC's atomic structure, frozen in place.
Frozen is a good word for it. Effectively frozen in time within the atomic spins. And then the final, absolutely critical step, retrieval.
You got it back out.
They got it back out. By simply turning the control laser beam back on, they could coax the atoms to collectively re-emit the stored light pulse. And here's the kicker. The pulse that emerged was, as far as they could measure, identical to the one that went in. No measurable loss of fidelity. So this proves it. Light, the thing we thought was immutable, the carrier of information, the yardstick of the universe, it can be stopped, stored in matter, and released. This fundamentally changes how you have to think about information, and specifically, the integrity of information as it propagates. Okay, so now we pivot. We've seen you can control light, even stop it. If light is the messenger, what happens to the message itself during that stopover? This brings us to quantum information theory and the king ideas of coherence and decoherence.
Right, because Einstein taught us photons aren't just energy packets, they encode events. Where something happened, when it happened, it's information. So if light is the main way information gets around, physically and even perceptually, then messing with it, stopping it like Hau did, opens the door to the idea that maybe the informational content itself could be affected before it gets processed or recorded somewhere else.
That's exactly the starting point for Lake's analogy. Now, coherence in quantum information theory, I think Nielsen and Schwann's textbook work here is all about preserving phase relationships.
Phase relationships, like the timing and alignment of waves.
Precisely. In a coherent quantum system, all the quantum waves are perfectly synchronized. This allows for things like superposition, a quantum object being in multiple states at once, which is fundamental for quantum computing and, conceptually, for perfect information transfer.
Okay, so coherence is good. It's order, synchronicity.
It's the state you need for reliable quantum processes. Decoherence, then, is the enemy. It's what happens when that perfect quantum system interacts with its messy, uncontrolled environment.
The outside world interferes.
Right. The environment essentially measures the quantum system, destroying the delicate superposition, scrambling the phase relationships. The synchronicity is lost.
So Howe's experiment, stopping and restarting light, was actually an act of managing decoherence.
You could say it was a demonstration of controlled decoherence and then recoherence. They managed to isolate the stored information within the atomic spins, shielding it from environmental decoherence just long enough to successfully retrieve the light pulse.
But Lake's theory seems to latch onto that interruption itself. Even if Howe retrieved the pulse perfectly, the fact that it was stopped, that there was this temporal break, that's the vulnerability.
That's where he introduces the idea of a potential phase offset. Even with Howe's incredible control and near-perfect retrieval, the theoretical model suggests that any temporary halting of a signal, any interruption, introduces a tiny, perhaps even currently immeasurable risk, a risk of slight shifts in the phase relationships, or the overall coherence of the information channel.
Okay, why are these tiny phase shifts such a big deal in this theory? Aren't they just minuscule timing errors?
But in quantum information, phase is information. Think of phase relationships as the internal clock and coordinate system for quantum data. They dictate how quantum waves interfere, which is fundamental to encoding. Imagine encoding data not just as zeros and ones, but by the precise arrival time of a photon relative to some reference clock.
Right, like quantum Morse code based on timing.
Sort of. Now, if that photon gets paused and maybe gets held for just a femtosecond, a quadrillionth of a second, longer than perfectly expected before it's released.
Its timing relative to the clock is off.
Exactly. Its timing is off, which means its phase relationship to the reference is altered. You've introduced a phase offset.
Okay.
And the really crucial idea in Lake's conceptual framework is that this tiny, seemingly negligible phase offset doesn't necessarily just vanish or average out. In a really large, complex, interconnected system like, say, the universe, or maybe a global fiber optic network, that tiny initial drift could potentially propagate. It could accumulate over vast distances or long times.
So the fact that information propagation is sensitive to these controlled stops, this idea of a phase drift that could build up, that's the specific physical concept Lake uses to make the leap to things like collective memory.
It provides the physical analogy, the framework. It suggests that if the very channel carrying information of the fabric of space-time communication, if you like, is susceptible to having its phase subtly modified, then any large-scale system that relies on that channel for synchronization is potentially vulnerable. Vulnerable to systemic discrepancies in the information it receives and processes.
It gives a potential physical basis for systemic synchronization errors, beyond just saying people misremember things.
Exactly. It offers a language rooted in fundamental physics to talk about how systemic information glitches could, in principle, arise.
All right, let's pivot to the other side of this analogy. The cognitive phenomenon, collective memory divergence. Most people probably know this better as the Mandela Effect.
Right. The term comes from the surprisingly large number of people who share a distinct memory of Nelson Mandela dying in prison back in the 1980s, when, of course, he was released and lived until 2013. But it's not just that one example.
No, it's countless things. Pop culture details, brand names, historical events.
And as researchers like Harrelson and Stone pointed out, these aren't just random individual memory errors. They're often very specific, shared, systematically varying memories across large populations who have no direct connection. It suggests some kind of common but incorrect memory template being accessed.
Let's use the classic example to make it concrete. The children's books. Millions seem to vividly remember them as the Berenstain Bears, spelled with an E.
Right, a clear, specific memory.
But the actual title, easily verifiable on any book cover, is the Berenstain Bears with an A. Where does that shared E memory come from?
That systematic shared discrepancy is exactly the kind of thing Lake is trying to find a conceptual model for. Now, cognitive science absolutely has explanations for memory errors. Daniel Schachter's work, for instance, clearly shows memory isn't like a video recording. It's fundamentally reconstructive.
Meaning we rebuild memories each time we recall them.
Pretty much. We rebuild them based on the original fragments, but also heavily influenced by our current knowledge, context, suggestions from others. Schachter's 7 sins of memory, things like suggestibility, bias, misattribution, show how easily our individual memories can be shaped and distorted, even systematically within groups.
Okay, psychology explains why my memory might be faulty, or why a group talking together might converge on an error. But the Mandela Effect seems different. It's the sheer scale, the synchronicity of the same specific error across millions of disconnected people. Why Berenstain, with an E for so many, psychology struggles with that specific shared detail, right?
That's the perceived gap, yes. Why the same incorrect detail arises independently in so many minds. And this is where Lake introduces his analogy, prompted by something he found intriguing: the timing.
The timing.
He explicitly notes this temporal alignment in his paper, the early 2000s. This period saw Hau's groundbreaking light-halting experiments 99 and 01, which dramatically demonstrated this potential fragility, this controllability of information propagation at the quantum level. And concurrently, the early 2000s was also when awareness and discussion of these collective memory divergences really started to take off online. The term Mandela Effect itself emerged later, but the noticing of these shared discrepancies accelerated then.
Okay, I have to jump in here, though. Skeptic hat on. Linking a physics lab experiment in Boston with millions of people online suddenly realizing they misremember movie quotes. Isn't that a massive leap? It sounds a bit like finding patterns after the fact. Correlation, not causation, surely.
That's a completely fair and necessary critique. And Lake himself is very careful about this. He explicitly states no causal relationship is established. The temporal alignment isn't proof. It's not evidence A caused B.
So what is it then? Why mention it?
He uses it more as a thematic justification, an invitation for interdisciplinary thinking. The argument is more subtle. If the fundamental carrier of information, light, was being manipulated in unprecedented ways at the quantum level right around the time that large-scale systemic confusion about shared information, memory, started becoming more visible, then maybe the physics of that manipulation offers the most rigorous available framework for modeling the memory phenomenon.
Okay. So the timing coincidence isn't proof, it's intellectual permission. Permission to apply the hardcore math and concepts of quantum optics phase stability, coherence to the much softer seeming problem of why people misremember the same things.
Precisely. It shifts the focus. Instead of just debating psychology versus poor memory, it allows us to ask, could there be a model based on the physics of information itself that describes how such systemic informational shifts might occur and propagate? Lake argues that quantum principles of coherence and signal integrity offer exactly that, a mathematically sound structure.
So we move from blaming the rememberer to modeling a potential glitch in the information channel itself.
That's the essence of the conceptual leap, yes.
Yeah.
Okay, let's bring it all together. We need to connect the quantum observation, stopping light might cause tiny phase offsets, with the cognitive puzzle, lots of people sharing the same wrong memory. How does Lake build that bridge?
The starting point, as I understand it, is to stop thinking of human memory and perception as purely individual, isolated things. Instead, view them as part of a vast, interconnected, global information network.
Exactly. A network that implicitly relies on information carried ultimately by light, whether through our eyes or fiber optics, propagating stably and reliably.
Okay.
So the quantum level interruptions, the things Hau demonstrated like storing light, the potential for phase shifts or coherence glitches.
Yeah.
These serve as the conceptual model, the analogy, for how errors might arise and spread within that global cognitive or informational network.
Let's go back to Berenstain Bears. The original information, the correct spelling Berenstain, is out there. It propagates through various channels, books, word of mouth, eventually the internet.
Right. Now, Lake's analogy suggests, what if, somewhere along those complex pathways, the signal representing Berenstain encountered some kind of systemic phase offset, a tiny, consistent timing glitch during transmission or processing across the network?
Then the process of receiving, integrating, and reconstructing that memory might systematically spit out Berenstain instead.
Conceptually, yes. The idea isn't that the memory recall is flawed, but that the input signal itself was subtly but systematically altered during its journey through the network before it even got to the stage of being integrated into memory. This potential modification of data fidelity during propagation is the absolute core of Lake's proposal.
And the early 2000s timing becomes relevant again here, not just for the physics experiments, but for the nature of that network.
Absolutely crucial. Because what else exploded in the early 2000s?
Yeah.
High-speed, light-based global communication.
Fiber optics, the internet backbone. Suddenly, everything was connected at light speed, carrying enormous amounts of synchronized data. Financial markets, news, GPS, everything.
Exactly. Now think about those systems. They rely utterly on light signals, propagating through fibers, switches, routers, complex physical systems. If those underlying light signals are, as the physics suggests, theoretically susceptible to tiny, maybe individually undetectable, phase drifts.
Introduced just by the process of bouncing around the network, being switched, maybe even tiny environmental effects.
Then those minimal errors don't necessarily stay minimal. In a highly interconnected, synchronized global system, they could potentially cascade.
A hypothetical cascade. A minuscule timing error, a femtosecond drift, in one critical network node.
Could theoretically propagate. Because so many systems depend on incredibly precise time synchronization. GPS needs nanosecond accuracy. High-frequency trading relies on even finer timing.
Ah.
A cascade of tiny phase offsets could hypothetically create larger-scale systemic errors in things like timestamping, data ordering, information encoding across the network.
And since we humans increasingly use these digital and social networks to access information, form memories, and reinforce collective understanding,
Then those potential system-wide informational offsets, those synchronization glitches originating at a very fundamental level, could manifest outwardly as what we perceive as discrepancies in collective memory or historical records. It could look like a whole population's perceived reality needed a kind of systemic resync.
wow. So Lake uses this to argue that point we stated earlier.
Hmm.
If light-encoded information can be halted or phase shifted, it's conceivable that data fidelity gets modified during propagation.
Right. Providing that rigorous, though speculative, physical analogy for how something like the Mandela Effect might arise not from individual minds failing, but from a subtle, systemic inconsistency in the information carrier itself.
So it's not just light traveling through empty space we need to consider, but light traveling through these vast, complex, human-engineered systems designed to manipulate and synchronize information. And the better we get at controlling light,
The more we might inadvertently reveal or even introduce these subtle vulnerabilities related to phase and coherence. It loops right back to Hau's experiments.
yeah,
She demonstrated the ultimate control, the storage. But in doing so, her work inherently underscores the sensitivity to decoherence. It highlights that phase relationships are paramount, and tiny accumulating phase shifts could, in principle, compromise information integrity over time or distance.
and then the final piece, collective cognition. Lake's theory stresses that these large networks, whether human social networks or digital ones, are really good at amplifying tiny initial inconsistencies, turning a potential femtosecond physics glitch into a decades-long argument about a movie line or a brand name.
That amplification within the network is key to bridging the scale from quantum effects to mass phenomena.
This whole framework really forces you to question the stability of the information we just take for granted every day. But we have to circle back and hammer this point home again. Lake is adamant, and we need to be too. This is an analogy.
Absolutely. It is not a claim that BEC experiments literally cause people to misremember book titles. That's not the assertion.
The value isn't in claiming causality.
No, the real value, I think, is that it provides a potential pathway for genuinely rigorous interdisciplinary research. It gives cognitive scientists grappling with collective memory phenomena a set of tools and concepts borrowed from quantum physics.
And maybe vice versa. It encourages physicists thinking about quantum information to consider how subtle effects might scale up in complex real-world networks.
Exactly. You can imagine, for instance, designing specific tests, maybe using computational models or even actual quantum networks to see how introducing controlled decoherence events or deliberate phase shifts in light-based information channels actually affects memory encoding or information retrieval within those controlled systems. It makes the abstract problem potentially testable, at least in principle.
So it takes the Mandela effect out of the realm of just anecdotes in psychology and offers a potential physical modeling framework.
A powerful conceptual tool, yes. Grounded in Hau's incredible experimental work, showing unprecedented control over light, the information carrier. Lake then takes that physical reality and uses it to underscore just how fundamentally important things like coherence, phase alignment, and information integrity are. Not just in quantum labs, but potentially in all large-scale systems that communicate and remember, digital or biological.
Because if the basic integrity of the information channel itself can be compromised, even slightly, even temporarily,
Then the fidelity of whatever you get out at the other end, whether it's retrieved memory, a historical account read online, data from a sensor has to be viewed with a certain theoretical suspicion. At least you have to acknowledge its potential vulnerability.
it reminds us that the constants and stability we rely on might only hold true under ideal conditions.
And in a complex universe or even just a complex global internet, how often are conditions truly ideal? Light travels astronomical distances, interacts with gravity, passes through engineered systems.
Yeah.
The potential for tiny cumulative phase drifts over time and space is, well, it's non-zero. It raises profound questions about the absolute stability of any information record, really.
So we'll leave you with this final thought to mull over, spinning directly out of the implications of Lake's Hau correlation. If the integrity of data, think about the historical data encoded in light from a star that exploded billions of years ago, or maybe the sensory data that formed your own earliest childhood memories, if that integrity is shown, even conceptually, to be sensitive to these kinds of temporary interruptions and phase shifts at the most fundamental quantum level. Well, how truly confident can you be in the absolute pixel perfect fidelity of any information that has journeyed across vast cosmic distances, or even just through our complex light speed digital networks over deep time? It certainly makes you wonder what almost imperceptible phase drifts might have already accumulated, propagated, and subtly shaped the very systems we use to define our reality.